We use exponential models to model growth and decay, and often it's population growth. And mathematically, exponential growth is a growth rate of a function that is proportional to its current size. Okay, so what does that mean? It means the more people there are, the faster the population grows. So it starts out slow and it increases more and more rapidly, which, as you remember, matches what the graph of an exponential function does. Looks like that, right? Okay, so the model for exponential growth is in the form of n of t equals n sub 0, that's the initial amount or population, times e raised to the rt. Now, if this looks vaguely familiar, it's the same formula that we use for continuous compounding of money. All right, it's exactly the same thing. So this is your initial amount. This is your final amount after t years, days, whatever. And r is your growth rate. So here's an example. The population of the Philippines in 2003 was 80 million. So that's our initial amount. We'll do it in millions. Population increases 2.36 per year. So r is positive 2.36. Whoop. It has to be in decimal form. So it's 0.0236. What's the population in 2020? So that means t is going to be 17 because 2020 is 17 years after 2003. So here we go. N equals 80 e to the 0.0236 times 17. And of course, this is a calculator question. So here we go. 80, and then I'm going to use my e to the x function, which is over the natural log button, and I put in 0.0236 times 17, enter, and we get 119.5. Okay, so we're at 119.5 million people in the Philippines in the year 2020, assuming that the population continues to grow at 2.36%. Okay, so if the amount of something is decreasing or declining over time, then instead of exponential growth, we have exponential decay. Now, guess what? It's the same formula. We just have a negative r instead of a positive one. All right, so here's an example. Potassium-42 is used to help diagnose brain tumors. The half-life of potassium-42 has a half-life, well, potassium-42 is 12.36 hours. Determine the exponential decay model that represents the mass of potassium-42. All right, so here we go. I'm going to use m because we're talking about mass, but you can use n again if you want. So m equals the initial mass times e to the negative rt. Okay, so we know that after 12.36 hours, we have exactly half. So 1/2 equals e to the negative r times 12.36. Now I'm going to take the log of both sides, and I'm going to use natural logs, because remember, the natural log of e to the x is x. So if I take the natural log of this whole thing over here, I get negative 12.36 r. And I can use this to solve for r. So let's get our calculator up. So I'm going to do natural log of 1/2 divided by negative 12.36. And I get r is 0.05608. 0.05608 equals r. Okay, so now we know what our model is. M is m sub 0 e to the negative 0.05608 t. So continuing with this example, let's say we're starting out with 500 milligrams of potassium, and we want to know how many are going to be left after 48 hours. So m equals 500 e to the negative 0.05608 times our time, which is 48 hours. Bring up our calculator, and I'll go 500 second e to the x negative 0.05608 times 48, and it looks like we're going to have 33.9 milligrams, which is 34 milligrams left in the system after 2 days. So that's how you use exponential growth and decay.